Okay, we are about to begin a new chapter, chapter 18, which is called carboxylic acid derivatives. We just spent a lot of time learning about carboxylic acids, and now we're going to spend a little bit of time learning about their derivatives. There are numerous derivatives, and the first thing we'll do is we'll look carefully at the structures of the common carboxylic acid derivatives. We'll then spend quite a bit of time talking about the reactivity. It turns out that the main reactivity of carboxylic acid derivatives is the so-called nucleophilic addition-elimination reaction, and fortunately for us, the mechanism of these are all virtually identical, although there's a lot of different specific reactions and a lot of different outcomes. The nucleophilic addition-elimination reaction has this recurring, very easy to understand mechanism, and we'll go through it in some detail. Once we do that, we're going to look at the specific case of various carboxylic acid derivatives and how they behave in these nucleophilic addition-elimination reactions. That's going to include acid chlorides, which it will turn out are the most reactive of the carboxylic acid derivatives, anhydrides, which are second most reactive, esters, which are third most reactive, and finally amides, which are the least reactive of the common carboxylic acid derivatives. Finally, we'll look at some additional reactions. So we begin up here with structures of these various carboxylic acid derivatives, and I suppose I gave some of it away already by talking about which ones were most reactive and which ones are less reactive. But hopefully you remember the structure of a carboxylic acid. That's sort of the parent compound or the parent functional group that can give rise to all these other carboxylic acid derivative species. They're all acyl derivatives because they all have that carbonyl, carbon doubly bound to oxygen. So for example, we recently learned that if you take a carboxylic acid and treat it with thionyl chloride, you can produce the corresponding acid chloride. And that acid chloride is going to be amongst the very most reactive carboxylic acid derivatives, so we're going to take great advantage of that when we look at our nucleophilic addition-elimination reactions. We also know that you can perform a Fischer esterification on a carboxylic acid, and I've done it here with an R' alcohol. We'd use excess alcohol with some acid catalyst, and lo and behold, we get the corresponding ester. There's the R'(O) of the R'(OH), the ester compound. We also know that it's possible to create methyl esters in a very different reaction, and that is a reaction with diazomethane. We talked about that one. That's going to give us the corresponding methyl ester quite nicely. How do we make anhydrides from carboxylic acids? Well, we're going to look at a couple different ways. Probably conceptually, the simplest way would be to heat carboxylic acids to very high temperatures, in which case you'd basically dehydrate two of them while condensing them together in the form of an anhydride. And then finally, we've also talked already about the formation of amides from carboxylic acids using amines in the presence of dicyclohexylcarbodiamide, or DCC. So look at the structures of each of these carboxylic acid derivatives and know them. Know when you look at them what the name of that particular functional group is, and by the end of this chapter, know how their reactivity stacks up one next to the other. So for example, the acid chloride, not surprisingly, has this very characteristic look with the chlorine attached to the carbonyl carbon. Know that an ester has a carbonyl group, a carbon doubly bound to an oxygen, followed by an OR. Looks very much like a carboxylic acid, which would be OH, except we replace the hydrogen with an R. There's a methyl ester, a specific example of an ester. Know that an anhydride is a unique functional group and that there are two carbonyl carbons in an anhydride molecule. And know that an amide has a nitrogen attached directly to the carbonyl carbon. Now I'm showing this as a secondary amide because it's attached, this nitrogen is attached to two carbons, but this could be an NH2 ending, it could be NHR prime like we've got here, or it could be two R primes, NR prime taken twice. All of those would be examples of amides. So we can have primary, secondary, or tertiary amides. So there they are. Those are the main carboxylic acid derivatives that we're going to spend some time talking about today. There's another species which you're also familiar with called a nitrile. This is an organic compound which has a carbon triply bound to a nitrogen. And you've seen this actually going all the way back into Organic Chemistry 1. These nitrile compounds were important, for example, when we studied SN2 reactions, because the cyanide anion could come in and displace a leaving group in an SN2 reaction to give a nitrile compound. We're going to talk a little bit more about these nitrile compounds. At first glance, they don't look structurally at all like the carboxylic acid derivatives, but it turns out that they definitely have some strong ties, chemically speaking, to carboxylic acid derivatives, so we'll talk more about that. So there we are. There's a good review of the way in which we can make these various carboxylic acid derivatives and a good review of their structures. What I want to do now is I want to turn back to our second bullet here. Our second bullet is all about the reactivity that these carboxylic acid derivatives undergo. And far and away, the most important reaction for the derivatives is the so-called nucleophilic addition-elimination reaction. So you had a little bit of a sneak peek of this in the previous chapter when we talked about converting carboxylic acids to amides using DCC. The first thing, if you recall, that we did is mechanistically we showed that DCC can react with the carboxylic acid to convert the OH group into a very good leaving group. And that then allowed a nucleophilic addition-elimination reaction to take place. That was just one isolated example. We're going to go through this chemistry in detail now, and hopefully, about 5 or 10 minutes from now, you really understand this reaction and how it works. So to do that, I'm going to go back, or I'm going to move over to this board over here, and I'm going to tell you that all of the carboxylic acid derivatives have this generic structure that I've shown right here. They've got something organic bound to a carbonyl group, and then I've got a leaving group over there, an LG. Now the leaving group can be a lot of different things. In the case of an acid chloride, it's going to be a chlorine atom, or the leaving group would actually be a chloride anion. If this were an ester, for example, then there would be an OR prime here, and the leaving group would be RO minus, or an alkoxide anion, etc. So the leaving group descriptor here, or label, is describing all of the carboxylic acid derivatives generically. What happens in a nucleophilic addition-elimination is that that carbonyl carbon, which we have long recognized as being electrophilic, will react with a nucleophile. And again, I'm being very generic about the nucleophile because there's going to be a number of different nucleophiles that we can use. But the nucleophile will come in, and this is the proper aeroformalism, starting with the electrons that are nucleophilic, bringing them into the electrophilic carbon atom. At that moment, we're forming a new bond to that carbon, but we'd be in violation of the octet rule unless we kick those pi electrons up to the oxygen. This is a very simple aeroformalism, but it is critical. Nucleophile comes into the electrophilic carbon, knocking the pi electrons up to the oxygen. That then leads to this tetrahedral intermediate. Those reactants, electrophilic carbonyl carbon and nucleophile, will be in equilibrium with this tetrahedral intermediate. This is truly an intermediate, like a carbocation intermediate, probably not quite as high in energy as a carbocation, but an intermediate nonetheless in the sense that it's going to have a very short lifetime. It's not going to stick around for very long. The reason it's not going to stick around for very long is it doesn't have to. There are more stable species that can form. What will happen is once the tetrahedral intermediate has been formed, one of these lone pairs, it doesn't really matter which one you pick, will bump back down to reform that carbon-oxygen pi bond. That carbon-oxygen pi bond in a carbonyl group is unusually stable as pi bonds go, so there's definitely a thermodynamic driving force, an energetic driving force to want to get there. When that happens, this carbon would be in violation of the octet rule unless it loses a bond to something that's already there. Now, if you look at the tetrahedral intermediate, what can it lose a bond to? Well, clearly I'm showing that it tosses out the leaving group and the leaving group takes the 2 electrons with them. So clearly the leaving group is the most likely suspect. But there are other bonds that are attached here. For example, the nucleophile that just came in principle, you could lose that. And that, of course, happens all the time. That just takes you right back to where we started. The only other option is to lose an organic group maybe this is a methyl group or an ethyl group or a phenyl group, but that's never going to happen because those sorts of groups are just terrible leaving groups. So realistically, the only two things that can happen is that the lone pair comes back down, reforms the pi bond, and you either toss out the nucleophile, which you just added in, which takes you back here, or you toss out this LG, this leaving group, which takes you in a new direction out here to this new acyl derivative, plus, of course, the leaving group anion. What's going to determine the success of this reaction to a large extent is the nature of that nucleophile. Is it a strong nucleophile? Is it a weak nucleophile? And the nature of that leaving group. Once we get to the tetrahedral intermediate, if we have a very good leaving group, it's going to fly in this direction to this new acyl derivative. This is the nucleophilic addition elimination mechanism. It's fairly simple as our mechanisms go, but really important, really, really important. And what governs whether or not this equilibrium lies to the right towards this new acyl derivative, our product, or to the left, back over here to reactants, what governs the position of the equilibrium is all the things we've been talking about. Well, let's move back to the middle board here, and now we can a little bit more appreciate what has been written. Because we talked about the fact that in this nucleophilic addition elimination reactions, not all acyl derivatives, not all carboxylic acid derivatives react similarly. Some are much more reactive than others. And let's look at this list. I've got it written down here from most reactive to least reactive. And what we're going to see, if we look at it carefully, is that the reason that the acid chloride is the most reactive is that it's got the best leaving group. I'm going to go ahead and I'm going to put a box around that leaving group. That's certainly one of the reasons that the carboxylic acid is quite reactive. It's not the entire reason, though. Another thing that happens with the carboxylic acid chloride, this acid chloride, is that the chlorine is a very electronegative atom, so there's going to be a bond dipole moment moving from carbon to chlorine, making the carbon even more electrophilic. It's already electrophilic because it's part of this carbonyl group, and we've long appreciated that carbonyl carbons are electrophilic. We can draw resonance forms which place a formal positive charge on carbon. So we've gone over that a lot with aldehydes and ketones and carboxylic acids, and now with carboxylic acid derivatives. That certainly plays a role. But having an electronegative halogen atom right next door further ramps up the electrophilicity of that carbon. So it's both of those things. The carbon is super electrophilic because it's part of a carbonyl and it's attached to a chlorine. And the chlorine is a really good leaving group. All combined, that makes the carboxylic acid chloride, or more commonly just the acid chloride, a very reactive carboxylic acid derivative. Next would be the anhydrides. Now, we haven't seen a whole lot of anhydrides before, but in a nucleophilic addition elimination reaction, this entire piece right here would be the leaving group, assuming our nucleophile came into this carbonyl right here. We'd form that tetrahedral intermediate and then spit out that leaving group. And if you look at it carefully, what is that leaving group? It would be a carboxylate anion. These two electrons would move on to the oxygen, and you'd form the carboxylate anion, a resonance delocalized anion. We just studied carboxylic acids, and we know that when you deprotonate a carboxylic acid, you form a carboxylate anion. There it is. Why is it a good leaving group? Well, mostly it's a good leaving group because it's a resonance delocalized anion. Resonance delocalization is very favorable, of course, and that makes it a pretty good leaving group. It's second most reactive. Moving further down, we've got these esters. In this case here, the leaving group in a nucleophilic addition elimination reaction would be an alkoxide. We'd form the tetrahedral intermediate. When the nucleophile came in, the electrons hop back down to reform the carbon-oxygen pi bond, and these two electrons would get knocked onto that oxygen to form an alkoxide. Alkoxides are not great leaving groups. Certainly, they're not nearly as good as the carboxylate anions or the halide anions. So alkoxide anions are strong bases, they're good nucleophiles, but they're not great leaving groups, and that's why the esters are further on down here in the reactivity axis. And then finally, all the way down here, the amides. These are the least reactive in a nucleophilic addition elimination reaction because what you'd have to spit out is some sort of a negatively charged nitrogen species. If it were just an NH2 out here, this would be amide. You might remember sodium or potassium amide. We've actually used that as a reagent, for example, with alkyne chemistry. If we have a terminal alkyne, we can bring in a strong base like a sodium amide and pull off that proton. The reason that the NH2 anion, the amide anion, is so basic is because it's not particularly stable. Things like the carboxylate anion, which are resonance delocalized anions, or the halide anions, which are stabilized by the great electronegativity of the halide, those are relatively stable anions. They don't mind, those are situations where the negative charge is held nicely. Over here with the amide anion, it's not a particularly stable anion, which means it's going to be a very strong base. As a base, that's great, but as a leaving group, that's going to hurt us. It's not a good leaving group at all, the amide anion. And that's true whether it's NH2 or NHR or NR2. All of those nitrogen-like amide anions are going to be poor leaving groups. So those are the least reactive, the amides. So there we have it. In total, the nucleophilic addition elimination reaction, acid chlorides, anhydrides, esters, and amides in that order. Now let's go over here and look at a couple specific examples. Last time I'll show this particular board here, you can see, as we've already discussed, that the carboxylic acids can be converted to a number of different carboxylic acid derivatives, and there are the reactions. Now I want to focus on that acid chloride. Why do I want to focus on the acid chloride? Because it is the most reactive of the carboxylic acid derivatives. From a synthetic perspective, if you're going to focus on any of the carboxylic acid derivatives in order to do nucleophilic addition elimination chemistries, this is the one. The carboxylic acids are quite reactive. You can get them to undergo a whole host of reactions. So let's look at it right now. I think what I'll do is I'll talk about a specific carboxylic acid derivative. We'll get rid of the R groups here just to give it a little bit more flavor, a little bit more meaning. So let's just say that you go into the laboratory and you pull out a bottle of benzoic acid. The carboxylic acid itself, the benzoic acid, isn't going to do nucleophilic addition elimination chemistry at all. We're going to have to convert it into one of those carboxylic acid derivatives, and we've just discussed the acid chloride is a great way to go because it's such a reactive species. So let's go ahead and convert it into the corresponding acid chloride, benzoic acid, and there it is. Simple reaction with thionyl chloride. Now, because of the great reactivity here, it turns out even if you just react the carboxylic acid chloride with water, you are going to get a reaction. The water is not a terribly strong nucleophile, but the acid chloride has got such an electrophilic carbon that even the weakly nucleophilic water will react. And you will quickly convert the acid chloride to the corresponding carboxylic acid. Well, that's actually where we started, so that wouldn't be terribly useful, synthetically speaking, but you need to know that this reaction will take place, and it is a nucleophilic addition elimination reaction. If you wanted to prepare an ester, one possibility would be a Fischer esterification of the carboxylic acid. We've talked about that in the last chapter. Another possibility, however, is to take the acid chloride and to react it with an alcohol. That will straight away convert the acid chloride into the corresponding ester. So far we've seen that it is very easy to convert the acid chloride into either a carboxylic acid or into an ester. If we go ahead and react this with an amine, we now have a very convenient way to make the corresponding amide. the same amide directly from the carboxylic acid using DCC. And of course, what the DCC does is it converts the OH group into a good leaving group. Well, actually, that's what we're doing here. We're converting the OH group into a good leaving group using thionyl chloride in the first step, and then reacting it straight away with the amine to give the corresponding amide. No need to use DCC here because we've already got a good leaving group once we've converted the carboxylic acid to the acid chloride. What else? Speaking of cyanide anion, turns out it's a really good nucleophile. We knew that back from SN2 days. And you can do a nucleophilic addition elimination reaction with a cyanide anion in order to prepare the corresponding acyl nitrile. There's another reaction. What if we wanted to make an anhydride? We haven't shown how to do that yet. Well, it turns out that if you take that acid chloride and you react it with a carboxylate anion, so there's the carboxylate anion, which we can produce directly from some carboxylic acid. Just by deprotonating it with a base, we can produce the carboxylate anion. We talked about in the carboxylic acid chapter that the carboxylate anion is not a great nucleophile, but again, the acid chloride is so reactive, it doesn't really matter. Super electrophilic carbon there because of the chlorine, because it's a good leaving group, because it's electronegative. All those things make it such a strong electrophile. We can do a nucleophilic addition elimination reaction with a carboxylate anion and an acid chloride in order to give us an anhydride. All of these nucleophilic addition elimination reactions are possible because the acid chloride is so reactive. What if we'd chosen a different carboxylic acid derivative? What if we'd taken our carboxylic acid and converted it to an amide using an amine in DCC, for example, and then tried to run all these various reactions? What we'd find is that they don't work. They don't work because the amide doesn't have a good leaving group and it's not nearly as reactive as the acid chloride. Likewise, if we converted it to an ester, several of these reactions wouldn't work. If we converted it to an anhydride and tried all these reactions, we'd probably get most of them to work because the anhydrides are a bit more reactive. But far and away, the easiest way to produce all of these acyl derivatives is to first produce the acid chloride. Now, we're going to look at the mechanism of several of these reactions. I'm not going to show you all of them because they really are all exactly the same. The only thing that's changing is the nature of the nucleophile. In this case, water is the nucleophile. Here, the alcohol is the nucleophile. Here, it's the amine, and in particular, that lone pair on the nitrogen of the amine that is nucleophilic. Here, it's the cyanide anion, and here, it's this negatively charged resonance delocalized carboxylate anion. All of those are nucleophilic species, and they're all going to undergo a nucleophilic addition elimination. Let's go back over to this board over here to see what the reaction will look like. Here's our generic reaction. Once again, the nucleophile is going to come in, attack the carbonyl carbon to form a tetrahedral intermediate. The tetrahedral intermediate will reform the carbon-oxygen pi bond, kick off the leaving group, and give us our new acyl derivative. That will be the mechanism for each and every one of those reactions we just drew over there. The only details that we need to add in are the nature of the nucleophile and the nature of the leaving group. As far as the leaving group is concerned, that's going to be chlorine because we're starting with a carboxylic acid chloride. Whoops, it's not a chloride anion yet. The leaving group will be a chloride anion once the nucleophile comes in. Let's look at the first reaction I showed over there, which was the reaction with water. Once again, water's not a very good nucleophile, but this is a super electrophilic carbon, so it is nucleophilic enough. Water will come in, attack the carbonyl carbon. That's going to have to kick up a pi bond onto the oxygen in order to avoid a violation of the octet rule. And we're on our way to tetrahedral intermediate. when the water adds in, you see that we do form an oxonium ion initially. And so there will be an extra step here compared to the mechanism I had before, because we've got to get rid of that acidic proton. This is still a tetrahedral intermediate, but this particular tetrahedral intermediate is likely to lose this acidic proton before it collapses back down to a new derivative. So here's the aeroformalism. Of course, we're going to bring in another molecule of water to do the work because we've added water. There's probably an excess of it. There's the aeroformalism to pick up the acidic proton off of the oxonium ion. We've certainly seen that quite a few times. Now we're ready to finish the reaction. This produces now a new tetrahedral intermediate. If you want to be thorough about it, you can say plus the H3O plus, which was created when the water picked off the acidic proton. This new tetrahedral intermediate is just going to collapse very rapidly in the same fashion we described, reforming the carbon-oxygen pi bond, kicking off the chloride anion as leaving group, and lo and behold, we have our carboxylic acid derivative plus chloride anion. Now at some point, the chloride anion and the H3O plus will team up and you'll generate some HCl. But there it is, nucleophilic addition elimination. Works really well with the acid chloride. I'm now going to go ahead and redraw another, or I should say draw another nucleophilic addition elimination mechanism, this time involving an alcohol to make an ester. Once again, we're going to start with an acid chloride, and I'm not going to be quite so generic about it. This time I'm going to write that we've got the acid chloride of benzoic acid, and we're going to allow this to react with an alcohol. Let's make it a 4-carbon alcohol, a butanol. Okay, so a very specific example. This is going to produce a butyl ester of benzoic acid, and here's how it will happen. You've got to visually recognize that you've got a carboxylic acid chloride, which is highly reactive in nucleophilic addition elimination reactions. You've got to visually recognize that you've got a nucleophile here. Alcohols are not great nucleophiles, that's for sure. If it were an alkoxide with an O- there, it'd be a great nucleophile. But as an alcohol, it's not a great nucleophile, but that's a really great electrophile, so it's okay. There's the aeroformalism. Here's the alcohol that's just added in. Notice that it started out with 2 lone pairs, but one of those is gone because it went to form the new carbon-oxygen bond right there. Once again, we've got an oxonium ion, so we're going to want to bring in another equivalent of alcohol to soak up the acidic proton. We've got our tetrahedral intermediates, actually 2 of them here, one as an oxonium ion, one after the acidic proton was soaked up by the alcohol, and there's the byproduct of that. We're going to allow the carbon-oxygen pi bond to reform, knocking off the best leaving group, which is the chloride for sure. What are our other options? We could have knocked off an alkoxide, but as we've discussed, they're not very good leaving groups. Or we could have knocked off a phenyl group as a phenyl anion, and that's just a horrible idea. That's a really bad leaving group. So the best leaving group by far is the chloride. That's what's going to happen. And in this fashion, we have now produced the corresponding butyl ester. From the acid chloride to the butyl ester, it's one pot. You throw the alcohol in, and this happens pretty quickly. The acid chlorides are reactive, so these reactions are very fast. Now, in these last 2 examples, I took an alcohol and before that water and just added it to the carboxylic acid chloride, and voila, you had your product. That tells us that we've got to be very careful with these acid chlorides. They are sufficiently reactive. We don't want to introduce them to nucleophiles like water that might be fortuitous on our glassware, if we were using wet glassware, for example. We have to be careful about how we run these reactions so that we don't get unwanted reactions. But if you want to derive the carboxylic acid from the acid chloride, for sure, hit it with water. If you want to derive the ester, any ester, from an acid chloride, for sure, hit it with an alcohol. Let's look at one more example. Let's show formation of the anhydride. What am I going to do? Well, I'm going to allow my carboxylic acid chloride to react with a carboxylate anion. You're going to have to prepare this in a separate step, but it's easy to do. You take a carboxylic acid, you treat it with a base like sodium hydroxide, and boom, you've got your carboxylate anion. Now allow your anion to react with your carboxylic acid chloride. It's a nucleophilic addition elimination reaction. Again, exactly the same as all the others. Here comes the nucleophile, pop up the pi electrons onto the oxygen. That will give us our tetrahedral intermediate, which looks like that. There's our leaving group, and there's our carboxylate anion, which came in and now is covalently bound to the tetrahedral carbon. This time you're not producing an oxonium ion because you started out with a negatively charged species here. So all you have to do is reform the carbon-oxygen pi bond, kick off the chloride, and you're there. There's your anhydride. In this particular case, it's a symmetric anhydride because I've got phenyl groups on both sides, only because I started with this acid chloride and this carboxylate anion. Nucleophilic addition elimination, really important. Mechanistically, in my opinion, compared to all the mechanisms you've seen, fairly simple, fairly straightforward. But it's a very important reaction because it converts one type of carboxylic acid derivative into all the other types. Now, I've mentioned that you can run the same reaction with anhydrides, with esters, and with amides, but of course the reactivity won't be the same. The acid chlorides are the most reactive. Let's see what would happen if we switched this up. Let's see what would happen if we switched this from an acid chloride to an ester. Well, to do that, all we have to do is get rid of the acid chloride here, and we're going to make it an ester. It doesn't really matter which ester we choose, just to keep things nice and neat. I'm going to choose a small ester, a methyl ester. I've switched my leaving group from a chloride to a methoxy, would be a methoxide leaving group. I'm not going to change the nature of my nucleophile here. My nucleophile is still going to be the carboxylate anion. It's going to come in. Presumably it's going to react. Now right away, it's not going to react as quickly because I don't have a chlorine there. I don't have that inductive withdrawal of electron density, and therefore this carbonyl carbon is not nearly as electrophilic as it is in the acid chloride case. So this first step is going to be slow compared to the last step, compared to the case where we had an acid chloride. It's going to slow down dramatically. My tetrahedral intermediate would look exactly the same, except that there would be an OCH3 here. Now, though, we've got an issue. Because if you look at this tetrahedral intermediate at this point, I can try to reform my carbon-oxygen pi bond, no question about it. But in order to get down here to my anhydride product, what has to happen is that I'm going to have to lose this bond, as I did before, producing a methoxide, not a chloride anion, but a methoxide anion leaving group. And that's not likely to happen, in all honesty. I'm going to put an X through this arrow right here, or next to the arrow, indicating that this is not a very likely reaction. Well, why not? Simply because as I reform my carbon-oxygen pi bond, the best leaving group I've got on this system is not the methoxide at all. It's the carboxylate anion. It's a better leaving group. It's a resonance delocalized leaving group. The place that this is most likely to go, or the direction in which this is most likely to go, is like this. Reform the carbon-oxygen pi bond and spit out the best leaving group, which is the carboxylate anion. That just takes us right back to where we were. That regenerates the methyl ester and gives us this nice resonance delocalized anion. Well, you can see right away why esters aren't quite reactive enough. Certainly not nearly as reactive as acid chlorides. We've talked about the reasons. The nucleophilic addition is not going to be as fast. It's going to be slowed down. And then once we get to the tetrahedral intermediate, there may be other options available, like in this case, which just send us right back from where we came. The likelihood that you get a large amount of anhydride product in this case is quite slim. So let's move back over here. We can run any of these reactions with any number of different carboxylic acid derivatives, but this reactivity ordering is really important. It tells us that we probably don't even want to try to run a nucleophilic addition elimination reaction with an amide. It's got such a lousy leaving group. Esters aren't a whole lot better. Anhydrides are reactive enough. If you had a lot of anhydride around, you could get nucleophilic addition elimination reactions to work nicely. But the best, by far, are the acid chlorides.